Planets are nice, but they are small, messy, and rare. In space, we can build habitats bigger than anything nature ever made. The question then isn't whether we can build giant space habitats, but rather just how big they can get before physics tells us no. Why stop at a space station? We can build homes bigger than planets. For over a century, science fiction engineering visionaries have toyed with the idea of habitats that don't just keep people alive in space, but create entire new small worlds, landscapes, not buildings, often the size of towns or entire counties. But our imaginations can conceive habitats larger and grander than anything nature ever gave us, and we wonder if we can build such things under known science. So today we're going to ask, how big could a space habitat get? We'll be focusing on megastructures designed specifically for living in space, giant artificial worlds that provide their inhabitants with air, water, farmland, and even gravity. A couple years back, we explored a wide catalog of such ideas in our Megastructure Compendium, a grand tour of cosmic-scale construction. Many of the designs we'll touch on today, from neo-cylinders to ringworlds and wardhouses, already have their own dedicated episodes where we dive deeper into engineering details. What we're doing here is bringing them together, comparing their scales, and asking just how large humanity's homes in space might ultimately become, what the constraints on their size are, and what tricks we have for getting around that. We'll also set aside one category for a brief skim today, as we gave it a longer discussion in our recent episode, Zero Gravity Habitats, Bubble Worlds, and Smoke Rings. Those bring their own scaling limits, mostly determined by the mass and density of their components, and they got their own dedicated episode last month. Here, our focus will be on habitats that try to replicate something planet-like, whether through spin gravity, massive enclosing shells, or sheer bulk. So let's begin with the basics. What makes a space habitat different from a space station, and what laws of physics decide how big we can make them? Basics of habitat scaling. When we talk about space habitats, we need to draw a line between a space station and a habitat. A station, like the ISS, is a machine, cramped, dependent on constant resupply, with life support more fragile than comfortable. A habitat, by contrast, is a home. It provides air, water, farmland, and gravity, not just survival but the comforts and scale of civilization. This does not necessarily have to be large or stationary. Nothing in space really is anyway, but we tend to assume many interplanetary ships, and certainly most interstellar ships, would have habitats aboard designed for long durations. Thus, while a habitat does not need to be a completely enclosed and self-sufficient ecosystem, we tend to assume they are either fairly self-sufficient or part of a wider conglomeration of habitats that are in total, much as a city and a farming community are not really complete without each other for trade. One could use a wider definition of habitat to mean many interconnected space stations, and we will look at some variations on that today too, but we try to limit habitat to a single large structure or directly connected sections a person could walk, swim, or fly to, and use terms like communities, conglomeration, clusters, or nations for the other. Now, to go from a structure to a habitat specifically, and excluding microgravity habitats that again we discussed recently, our first challenge is gravity. Without it, humans suffer bone and muscle loss, fluid shifts, and other health issues. Moreover, you are not going to have a realistic simulacrum of a terrestrial ecosystem without relatively normal gravity. Engineering an ecosystem based on low or no gravity might be an awesome task, a great challenge that might produce great wonders, and yet it won't be Earth-like. Now, planets provide gravity for free, but often not what we want or where we want it. But in space, we usually turn to rotation, or what we call spin gravity. Spin a cylinder, ring, or torus fast enough, and centrifugal force gives you a down direction. The larger the radius, the less spin you need, and the more natural it feels underfoot. People often wonder how we know this works, and we know it from every time we use a washing machine, which spins water out of your clothes by making the internal gravity higher to drip it down to the sides of the drum. Down in such environments points out, and up to the center, and you live inside on the interior of the drum. People often wonder how gravity works in space, so let's clear up a common misconception. The International Space Station, and everything else in orbit, does not actually escape Earth's gravity. In fact, at the altitude of the ISS, gravity is only a few percent weaker than here on the ground. Astronauts float not because gravity has vanished, but because they are in free fall, circling Earth sideways fast enough that their fall around the planet match the curve of the surface. The result is weightlessness, or more precisely microgravity. Now, what about inside a spinning habitat? If you jump off the floor, will you suddenly float? No. Just like touching the wall of the ISS does not change the pull you feel, jumping inside a spinning drum does not cancel your gravity. The centrifugal force from rotation keeps pressing you toward the hull. But is spin gravity identical to real gravity? Well, not quite. In a rotating frame, the pull gets stronger the farther you are from the center. Double the distance, double the force. Real gravity follows the inverse square law. Double the distance and the pull drops to a quarter. That means in both environments your feet feel a stronger pull than your head. But in a spin habitat, you need a structure at least 10 times taller than a person before that difference stops feeling strange. Larger habitats solve this by spinning more slowly to reach the same gravity, which also helps to avoid nausea. Like rotating planets, spin environments also come with some Coriolis effects, but they manifest differently. Try moving radially, inward or outward, and you find yourself deflected sideways. It's subtle in large cylinders, but obvious in smaller, faster spinning habitats. So when it comes to spin habitats, bigger really is better if the goal is to make the environment feel Earth-like. We generally prefer a rotation rate of 2 RPM or slower, and ideally closer to 1 RPM or less. That's 1 full spin per minute or even slower. And this is not going to make you feel sick or nauseous any more than turning around in your chair over the course of 1 minute would. At 2 RPM, you can generate 1 Earth gravity with a radius of about 224 meters or 733 feet. That is already a large structure, but dropping the spin to 1 RPM is even nicer for comfort. The catch is that at half the rotation rate, the required radius goes up with the square of the change. You need a habitat 4 times wider to get the same 1G. Keep that in mind for later, because in theory, the most natural habitat of all would be one so large it only rotated once per day, like Earth itself. A quick side note, while the spin rate in RPM gets slower as the habitat gets larger, the tangential velocity at the rim actually climbs sharply. It scales linearly. Double the radius and you double the rim's speed. The kinetic energy to spin it up grows even faster, with the square of that speed. In other words, a habitat twice as wide takes 4 times the energy to get rolling. Fortunately, space is a frictionless environment, so once set spinning, a habitat will keep turning for ages with only occasional boosts to make up for long-term losses. This is where we get our first 2 well-known structures, the von Braun wheel and its larger successor design, the Stanford Torus. The von Braun wheel itself is not what I normally call a habitat, merely a space station, at 125 feet in radius and only designed to produce weaker gravity akin to Mars, which is 38% of Earth's. The Stanford Torus is a design from a couple decades later when we were thinking about people living in space, not merely being stationed there for a while. It's over a mile wide, 1.1 mile diameter or a radius of half that, 894 meters, and that is the 1 RPM radius for normal gravity, so it's not an arbitrary design size. Bigger places cost more, but your raw materials for things like air, water, and soil for on the inside scale linearly with living area, so you can't just build bigger if you want to. Double the living area, double the budget for mass. And moving to design like the modified Bernal sphere, the original and much older design was actually a non-rotating microgravity habitat, or the O'Neill cylinder, which has a diameter of 5 miles or 8 kilometers, and is a long can or cylinder design, and comparable in size to the typical American county, of which we have about 3,000. So why can't we just scale habitats up endlessly? Well, physics sets limits. All that mass under spin is straining, and very akin to a suspension bridge, the same length as the circumference of that habitat. The materials begin to tear under their own weight. For a ring or cylinder habitats, tensile strength is the defining factor. For other designs like giant domes and shell worlds, which we'll get to later, it's compression and buckling under its own mass and gravity. The O'Neill cylinder is designed for using steel as your building material, and with lots of leeway for extra mass or damage. We could go bigger with modern steel and more with aluminum, or other even stronger tensile strength materials like Kevlar or graphene. We have some tricks for circumventing even these limits, but we'll get to them later too. Fundamentally, space gives us freedom to build bigger than any planet, but it also makes us answer to geometry, mass, and the stubborn rules of mechanics. Cylinder and ring habitats, linear and radial extremes. When most people imagine a space habitat, they don't think of a cramped station. They think of something sweeping, a vast cylinder or gleaming ring, farmland climbing the walls, rivers arcing overhead, sunlight pouring in from giant mirrors. These designs inspire because they don't just scale life support, they scale civilization itself. The O'Neill cylinder is the classic entry point, 2 counter-rotating drums, each about 8 kilometers wide and 32 kilometers long. A single O'Neill cylinder could house and support around 1 million people in comfort, though we tend to envision them a bit more rural, and more urban setups could push this into megacity scales. Now scale that up to the Bishop Ring, the big brother of the Stanford Torus, and the McKendree cylinder. These assume steel structures have been replaced with carbon nanotubes or graphene, and their radius could be 1,000 kilometers or more, with lengths to match in the case of the McKendree cylinder. Such a structure offers millions of square kilometers of surface, more than the continent of Africa, and enough for billions of people. Stand inside one and the horizon wouldn't just curve up a little, whole continents would hang overhead, glittering upside down the distance, though by now the atmosphere or atmocylinder is getting thick enough between you and the horizon to cause visual limits, so you're not seeing the horizon rise up, but probably more of a red twilight hazy band. Banks Orbitals. Scale further up and we reach the Banks Orbital, popularized in Ian M. Banks' cultural novels. It is not arbitrarily huge. With a radius of 1.84 million kilometers, considerably bigger than the Moon's orbital distance from Earth, it rotates just once per day to give you normal gravity, giving you natural 24-hour cycles, and then you skip all the mirrors or artificially powered lighting such habitats normally have. For every given day length and gravity combination, you have a specific radius these rings would be, with shorter days or lower gravity permitting smaller rings. Even in a modest 1,000 kilometer width, much less than a percent of its radius, a Banks orbital has surface area of 3 billion square kilometers, or 6 times the entire surface of Earth. Widen to 10,000 kilometers and you have a world with 60 Earths worth of land. You would not make this design arbitrarily long or cylindrical though, as getting sunlight in from the normal natural sun is the whole point, and anything much wider relative to its radius than a thick bracelet or watch band's proportions is going to interfere with that. So your maximum size here is on order of perhaps 2 to 300,000 kilometers, which would translate to 1,200 to 1,800 Earths worth of living area. And if you want more space with this habitat design, you just make more of them and put them in orbit of the same sun. You can, if you want, even have them chain linked together, but connecting them as a single habitat, when you could walk, swim, or fly to, gets pretty tricky. This structure does have its own dedicated episode if you want to know more about the internal appearance and geography. No known material could support this much strain, but we'll get to a workaround in a moment. First, let's push the size even further. Ringworlds. The Ringworld is the great dream of megastructures, a ribbon the size of Earth's orbit, 300 million kilometers in radius, with a habitable inner surface offering more land than 1 million Earths combined. Stand on it and the horizon will curve not gently upward, but forever. A sky framed by mega mountain-sized walls holding the atmosphere, with rivers and continents sprawling for light minutes around the star. It's a breathtaking vision from the brilliant mind of the legendary Larry Niven, but also one that critics often dismiss as impossible. The usual objection is material strength. To spin at 1g rotational speeds, the rim must endure tangential velocities of over 1,000 kilometers per second, and exert a tension on structural materials that no known material could survive, though the hypothetical material known as mag matter could. By conventional thinking, the stresses would tear it apart long before construction finished, and it would be spinning fast enough that its debris would actually be interstellar in its escape velocity. But as we've explored before, this problem is not insurmountable. The trick is to decouple the habitable band from the need to carry all that load itself. You don't build the Ringworld or the Banks orbital out of one miraculous unbreakable material. Instead, you nest this ring inside a far more massive and slower rotating outer ring. This ring and the outer combined would have a net angular momentum equal to what all the mass would normally need to orbit that star, circumventing one of its support problems, but more importantly, it will push back against the other ring. That ring is pressing down hard on the outer ring below it, but they are not touching and are separated by vacuum. You can magnetically keep it pushed apart and distribute the load to both. This outer ring can be filled with some nice cheap mass like hydrogen and helium, and also serve as a protective shield for the inner ring. I should note that this is orders of magnitude easier with the Banks orbital, and those do not have the issue of needing sun squares between the inner ring and the sun to block it out half the time for nighttime, or twilight bands for that matter. One neat thing about a Ringworld, and these also have their own dedicated episode, is that you can make a habitable Dyson sphere this way by having many rings, each a little wider or narrower than the last, so they don't quite touch, and tilted at an angle until the whole sun is englobed. Transporting these as a single habitat is also tricky but doable, offering you 2 billion times the total living area of Earth if done around our sun. This tends to be our upper limit on most megastructural conglomerations, as you need power to run life support on them, and the sun gives off 2 billion times the light that Earth needs, though it isn't a hard bar, and we'll get to ways around that today too. So while many will say a ring world is impossible, that's more a reflection of how daunting the scale is than a final verdict. With clever engineering and enough raw material to build entire planets into girders and stabilizers, it becomes less a fantasy and more a challenge. A ring world Dyson sphere would not be easy, but it remains a vision that fits within the laws of physics, provided we accept the structure as not a single ribbon, but a whole ecosystem of rings. That said, I think the Banks orbital would be as big as anyone would go, simply because it's already dipping into the BWC megastructure range, where an equal amount of living space could be done more cheaply among many more smaller habitats. A BWC megastructure incidentally is short for because we can, and refers to those megastructures who exist mostly to prove you can build it if you wanted to, rather than any real practical reasons. A cube-shaped planet, for instance, is doable but kind of weird except for novelty. A giant disk world or flat Earth is actually a borderline BWC, as they do have some practical advantages over traditional worlds that might fit some niche applications. Today we're getting a chance to see how we can engineer immense things in space, but what if we could also engineer time? In this month's Nebula exclusive, Chrono-Engineering, Manipulating Time as Technology, we look at the options under known physics and explore options from the edge of cosmology and sci-fi, from the very real time dilation we already correct for in systems like GPS, to the speculative end of wormholes, causality engineering, and what a civilization does when time becomes something you allocate. Every month for years now, I've released an exclusive episode on Nebula, along with other bonus content and extended editions, and right now, Nebula is offering a 3-day free trial for you to check them out. It's also where every episode of SFIA premieres early and without any ads or sponsor reads. Just use my link or the QR code on the screen, and you get 50% off a yearly plan. Just $30 for the whole year, about $2.50 a month. Head to go.nebula.tv/IsaacArthur and start watching today. The Topopolis. Now, practicality in building is a real concern, but rotating habitats can scale in more than one direction. A cylinder is really just a ring that's been stretched along its axis, and making a cylinder longer does not add structural stress the way making it wider does. That brings us to the Topopolis, another invention of Larry Niven, which keeps the same radius as a normal spin-gravity habitat, but can be made arbitrarily long. Imagine a tube only as wide as an O'Neill cylinder, about 8 kilometers or 5 miles across, but stretched out as far as you like. A Topopolis about 20 million kilometers long would have the same living area as Earth. Stretch it to 20 billion kilometers, and you have around 1,000 Earths of space. Push it to 20 trillion kilometers, and you're looking at 1 million Earths. But by then your Topopolis is over 2 light years long, stretched from one star toward the next. Happily, every material, no matter how rigid, eventually bends and knots like yarn if you make it long enough. Even spinning does not prevent that, so the Topopolis invites you to loop it around things. You could make one giant ring around Earth or Jupiter, or weave many loops together, or even create a tangled ball encircling a star, billions of kilometers of habitat in total length. It is also worth noting that there's no real reason for a rotating habitat to be exposed directly to space. Unless you want windows for sunlight, and honestly I doubt anyone would, you can sheathe the whole thing in a slightly wider, non-rotating sleeve. That outer layer could be filled with cheap hydrogen or helium for radiation shielding, or carved right into an asteroid by boring a cylindrical tunnel through it. In a Topopolis, this allows you to rest multiple rotating tubes side by side, like threads in a bundle, with transport systems linking them together. That way you're not limited to a single endless corridor, but can create a braided network of habitats, and indeed they are turning slow enough that it wouldn't be that hard to connect them together to the non-rotating floor. A home inside one could have a transport tube down its basement to reach the sheath, and you do not have to stick with O'Neill-sized tubes. If your materials allow, you can scale up. Carbon is more abundant than iron, so if you can bulk produce it, you might as well make graphene instead of steel. And a graphene Topopolis with 1,000 kilometers radius would only need about 80,000 kilometers, or 50,000 miles of length, to equal Earth's surface area. Stretch it into a Dyson-scale project, and you need 100 trillion miles of length wrapped around a star. That's about 17 light years, big enough to connect stars themselves. And why not? This is SFIA after all. With Schroeter thrusters, you can bring 2 stars to a relative stop and string a Topopolis directly between them, weaving a cosmic yarn ball that can engulf both in a great web of ribbon. You could literally walk, swim, or fly between a pair of suns. Topopolises, or Topopoli if you prefer, have so many options that we give them their own episode, but in basic form, life inside would feel like a river valley without end. Cities and farms strung like pearls along a highway that stretches into infinity. You could walk or boat downstream your entire life and never reach an edge, because there isn't one. Eventually it probably loops back in on itself anyway. From outside it might look like a tangled ribbon, circling planets or threading between stars. And best of all, none of this requires magic. Even stopping stars with Schroeter thrusters or modified star-lifting engines is just a matter of mirrors and magnets, scaled up to ridiculous proportions. It's epic engineering, but in terms of technology, simpler than a wristwatch. Planet-wrapping habitats. Now that we've covered rotating habitats, let's consider some alternate options. Not every habitat is to float freely in space. Sometimes the simplest approach is to take a world and wrap it up. Dome cities and valley houses. Perhaps the easiest option in a big habitat is simply to build a big greenhouse on a barren planet. The most modest step is covering smaller regions with domes. Individual cities, craters, or valleys can be sealed under transparent or semi-transparent roofs, making a patchwork of livable zones on an otherwise hostile world. This approach does not create new land, but it multiplies the amount of usable area on marginal planets and moons. It also scales flexibly, a handful of domes for a small settlement or thousands spread across the planet. Expand the dome concept and you get the world house, a giant greenhouse stretched over an entire planet. The roof could be a thin but strong film suspended kilometers above the surface, held up by towers, cables, or even the pressure of the atmosphere itself. Beneath it, the climate could be tuned to Earth-like conditions. A world house could make Mars habitable without waiting centuries for full terraforming. The challenge is not strength so much as heat management. A world house traps sunlight very effectively. Without shading systems and radiators, it quickly becomes a plant-sized oven, which also means it works on planets that are far from the habitable zone of that system. These structures do not need to be planetary in scale either. You could englobe an asteroid or a moon in the same way, providing atmosphere and climate control even in low gravity. One option for boosting surface gravity is to embed a small artificial black hole at the center. This assumes you don't already have some Star Trek-style artificial gravity. Natural gravity falls off with the inverse square of distance, so a tiny black hole inside an asteroid only 10 kilometers wide might give Earth-like gravity at the surface, but just 10 kilometers above that surface, the pull drops to a quarter of normal. And surface gravity isn't what keeps an atmosphere bound, it's escape velocity, which depends on total mass. For an object like this, the escape velocity would only be about 443 meters per second, just over the speed of sound, and about a 20th of Earth's. That means without the enclosing world house roof, the atmosphere would quickly leak away. Worse, if the roof cracked, the air would vent out at lethal speeds. Such a world would need a mass of roughly 1.5 times 10 to the 19 kilograms, about 1/400,000th of Earth's. The surface area would also be about 1/400,000th of Earth's, so the scaling works out neatly. If you want a miniature world with normal gravity using normal matter, you need its mass to scale linearly with its surface area. But to pack that much mass into something the size of a large asteroid, you need extremely dense matter, which is where black holes come in handy. Matrioshka Shellworlds. This episode is about building big, not small. And sometimes big means making a planet less dense rather than more. Saturn, for example, has nearly the same surface gravity as Earth, but with about 100 times the mass and surface area. Earth is the densest planet in our solar system, Saturn the least dense, yet both feel similar to stand on, ignoring that you can't stand on Saturn. Cover a Saturn-like world with a shell so you could, slow its rotation to give it a 24-hour day, and make it closer to the Sun, and you have a habitable planet 100 times larger than Earth. But there's no real upper limit. Wrap a shell around a black hole and you could build an Earth gravity world with 1,000,000 times Earth's living space, comparable to a ring world in scale. Unlike a ring world, though, such a shell can't rotate around a star to make day and night cycles. Instead, it would need artificial lighting, which is something a black hole is ironically well suited to power, thanks to the vast available energy from accretion disks or magnetic fields. The real efficiency comes from stacking, though. Each additional layer of shell adds only a little more mass, but creates a whole new world that shares the same gravity from the layers below. Since you have to do artificial lighting anyway, you just use the floor of the previous level as the ceiling and lighting for the one below. At the most ambitious end are Matrioshka Shellworlds, stacked artificial crusts, each with its own sky, land, seas, and atmosphere. Towering support pillars hold them apart, we call an Atlas pillar, with elevators or tunnels running between. A single planet might host dozens of these layers, each as expansive as a continent. Done right, Earth could be converted into a world that hosts trillions on its many stacked surfaces. The chief limitation is thermal. Every added shell blankets the one beneath, so managing heat flow and energy balance becomes critical. The most extreme version of this is the Birch planet, which has not just a few suns worth of mass like the typical black hole, but millions like the giant black holes in galactic cores, or even billions. See our episode on Kardashev 3 and galaxy-scale megastructures for more discussion of these. Planet-wrapping habitats give us the stability of natural surfaces with the flexibility of engineering. They are not as free-floating or modular as cylinders, but they let us turn the worlds we already have into multi-layered jewels of civilization. Alternative and exotic designs. I wanted to wrap up on some miscellaneous options beyond cylinders and domes, and the ideas from there on only get stranger. Some are highly practical, others are pure thought experiments, but all offer insight into just how flexible habitats can be. Asteroid colonies. The most obvious path is hollowing out asteroids. Carve out the interior, reinforce the walls, and start a rotating space habitat. The rock itself provides natural radiation and shielding, and you can keep drilling more as you mine the place out, and you can connect these to Topopolis, or just have exits that go into pressurized corridors between, or thinner rotating habitat corridors. You could cram thousands of habitats into one asteroid, and indeed widen out over time as you hollow it out for mining and dump unused material on the surface. These are not vast on their own, but with millions of asteroids in the belt, the cumulative living space could exceed Earth many times over. Buckyhabs. You can link multiple rotating habitats together in a variety of methods, the sausage link approach being the most conceptually easy to visualize, but you can also form a geodesic lattice, or buckyhab. The linkage by default would be a pressurized sphere, and the cylinders would narrow down toward their end caps, lowering their gravity as they narrow and enter into these pressurized microgravity junctions. These lattices can be many different varieties. Two-dimensional layouts as hexagons is a common one to discuss, but they can also be three-dimensional, and it is not necessary that all the halves have the same dimensions. Rung worlds. Another variation is the rung world. That's rung like a ladder, not ring like a ring world. A rung world, which really deserves its own episode, takes a number of rotating cylinder habitats and lays them out like rungs on a ladder. The long arms of that ladder might be a Topopolis, a pressurized microgravity corridor, or even an unpressurized transport spine. And in practice you can mix all of these. We often imagine the ladder bent around into a circle, perhaps encircling a planet or even a star. Unlike our ring world, a rung world does not need impossible tensile strength. It's entirely feasible with conventional materials, provided you have enough of them. As with a ring world, you can tilt and stack multiple structures at varying angles until they form a dense sphere around a star, creating a Dyson-like swarm. There's no hard maximum length for the rungs themselves. Each is simply a rotating habitat of arbitrary size. The radius of each, however, is constrained by the same strength limits as any O'Neill or McKendry cylinder. A rung world wrapped around Earth at geostationary altitude, for example, might circle the planet with its rungs, while the space in between was filled with solar collectors. Over time, more rungs and habitats could be added wherever needed, gradually building a complete belt of civilization. Rung worlds can, in principle, scale without bound. Their radius could go to truly astronomical proportions, even reaching Kardashev Type 3 levels. One might imagine a rung world framework not around a planet or a star, but around an entire artificial dwarf galaxy, each rung a world in itself, strung into a cosmic ladder of civilizations. Flat Earths and Alderson disks. We talked before about building flat Earths, which are not quite in the same league as the biggest megastructures, but still fascinating. We have an episode dedicated to challenges and options for actually constructing one, and while evenly distributing gravity across the disk is tricky, it can be done. The main reason to build such a world is that a coin-shaped planet can provide its own day and night cycle by spinning like a coin, and would have identical seasons everywhere. That means you could make an enormous resort world without wasting mass on undesired polar regions. There are limits on how large you can build one if you want to rely on rotation for lighting, but if you're willing to illuminate it with artificial sources, there is no fundamental size cap. At the farthest end of that concept lies the Alderson disk, a vast plate wrapped around a star, extending billions of kilometers in radius. Its mass would exceed that of all the planets in the solar system combined, and would need active support to keep from collapsing under its own weight. It is also a wildly inefficient way to capture starlight. A Dyson swarm would do that job better, but the Alderson disk represents one of the largest continuous surfaces ever imagined. While it's not a practical design, there are ways to make it doable, and it illustrates the principle that there's no clear upper bound on how big a habitat might be, short of stellar engineering. See our Flat Earth Megastructures episode or Alderson Disk episode for more discussion of these bodies and some interesting variants on them like the Sombrero planet. These alternative visions remind us that habitat can mean almost anything. From hollow rocks to geodesic networks to world-spanning plates, these limits are set less by physics than by imagination. So, we've pushed the boundary today a lot on what sizes might be possible, but would they be built much? My personal guess is most habitats built will be smaller, and moreover, not just in sheer quantity, but the majority of the total land area will be in these much smaller habs too. Same as we not only have more houses than skyscrapers, but way more total living area in houses than in those far fewer skyscrapers. And yet the BWC, because we can megastructure, is, in my mind, also very likely to be built, because civilizations like challenges, and in a Dyson swarm of a quadrillion O'Neill cylinders and smaller habitats, a few flat Earths represent a fairly trivial expenditure, a decent place to store helium for future use, and a tourist trap that people will want to visit. Now scale up from the immensity of Dyson swarms around our sun to the billions of other stars, and their own eventual Dyson swarms, and it becomes way more believable that megastructures of epic scale will be built sometimes, even when not very practical. You might have a galaxy where less than a trillionth the living area was cube-shaped planets, and a Kardashev 3 galactic civilization that would still mean a billion Earths worth of such cube worlds were hanging around. Ditto donut planets and flat Earths and more. But what we also saw is that often this scaling up is not impractical. Rung worlds and Bucky habs and Topopoli are no special feats of engineering, and may be just as easy as their equivalents in other habs to build, and have an obvious attraction. So, how big can a space habitat get? The answer ranges from a dome over a crater to a ribbon that loops between stars. Each step upward in scale carries new challenges, but also new wonders. What is clear is that we are not limited to the planets nature gave us. We can build our own, as large, as strange, and as many as we dare.